Great.
Uh,
Great. Good morning, everybody. So it's a great pleasure to have our next speaker in this seminar series. It's Istvan Tomon. Right, Istvan is a very bright young researcher. We're going together some long time. He spent some time in Switzerland, both in Zurich and in EPFL. So you can read his bio on the homepage of the seminar, and he will talk today about configuration of boxes. Please, Istvan.
So thank you for the invitation. Thanks everyone for joining. So indeed, this talk will be about problems involving configurations of boxes. So in general, we will have the following setup. We will consider a family B of axis parallel boxes in Rd, so the B-dimensional real space, where we think of D as some fixed constant, and we always consider just finite families. So we think of our families being big, while D is being small. So a typical example, as you can see, is the configuration of boxes in dimension 3. So axis parallel boxes are among the simplest combinatorial geometrical objects you can study in any fixed dimension. Yet still somehow configurations of boxes can be very complicated, and there are many very simple looking questions that are still open. So these questions involve, for example, this discrepancy, both combinatorial and analytic versions, epsilon nets, both weak and strong, coloring problems, Halley type problems, Ramsey type problems, and so on. So actually what happens is that for most of these problems, it is not very hard to come up with bounds that match up to logarithmic terms. But then getting rid of these logarithmic terms or deciding whether they are needed is somehow a notoriously hard problem. And this talk will be about a construction which shows that for many of these problems, you actually do need these logarithmic terms. So somehow these configurations of boxes can be more complicated than people conjecture. So what are these problems that I will talk about? So the first one is a Halley type problem for boxes. So as many of you may know, Halley's theorem is one of the classical results in geometry, which says that if we have some family of convex sets in dimension D, and you assume that any D plus one of them have a non-empty intersection, then the whole family has a non-empty intersection, so the whole family can be pierced by a single point. Now this is a quite stronger version for boxes, but which can also be proven much more easily. So in the case of boxes, in any dimension, it is enough to assume that any two of the boxes intersect, then you automatically get that all of the boxes intersect. So in other words, all the boxes can be pierced by a single point. Just to give you a picture, so here is a family of rectangles, which are boxes in dimension 2. Any two of them are intersecting, and you can find this red point here, which pierces all of them. So now Halley's theorem has a number of generalizations, extensions, strengthenings, and maybe one of the most famous is the so-called Hadwiger-Debrunner problem, which was famously solved by Allen and Clayton. So I don't want to go into details about what this problem for general convex sets is, but let me say what's the analog of it is for boxes, because it's even much simpler than the general case. So this theorem was first, this problem was first considered by Gerfash and Lahal, who proved that if we have a family of boxes and we assume that among any k plus one of the boxes, you can find two intersecting, or in other words, you don't have more than k pairwise disjoint, then you can pierce all the boxes by a constant number of points, where this constant only depends on k, so the number of pairwise disjoint boxes and the dimension d. So this is kind of this extension of this Halley type result where this was about the k equals 1, and now we look at what happens for larger k. And in general, Jarfash and I proved that one can choose fdk to be less than k to the d. So in what comes, we will assume that fdk denotes the minimum of this constant we can choose, so the optimal number of points we need for Pearson. So this argument is quite nice and quite simple. So actually, let me show you how you can prove this. So the k equals, so the d equals one case, in which case the boxes are just intervals. So it was already known much before. So this result is attributed to Galilei, but it was known even earlier. So it says that if you have a family of intervals and you don't have k pairwise disjoint, then you can pierce them by k points, and this is of course optimal. So now I will not prove this result, it's a nice exercise, but let's just use this result to show the general case. So suppose that we have this family of boxes. So now again, just in 2 dimensions. And now what we will do, we will project our boxes along all the possible coordinate axes. Then we get these systems of intervals. Now, an important observation is that if 2 boxes intersect, then the projected intervals intersect in every direction. So this means that if our family does not contain more than k pairwise disjoint boxes, then none of these systems of intervals contains more than k pairwise disjoint intervals. So in particular, we can find k points that pierces. So for each system of intervals, we can find k points that pierce them. Now what we do, we will just project these points back, and then so the projections. So the inverse image of these points is a hyperplane, and if you look at the intersections of these hyperplanes, we get a k by k by k by k grid, and one can easily check that this grid will pierce all the boxes. So this is a very simple proof. Okay, but now we are interested in is that how good this bound on fdk is. Can we improve this? Is this tight? So already in the 2 dimension, much before this result of Jarfash and Lyle, Wagner conjectured the very precise value of f2k, and conjecture that f2k is just 2k minus 1. So Jarfash and Lyle proposed a slightly weaker conjecture. So they just proposed that it goes that most linearly. But so somehow, surprisingly, the best known lower bound in 2 dimensions is 2k minus 4. So if you look at this conjecture of Wagner and this result, you might be a bit confused that, okay, so why did Wagner make this conjecture if he didn't even have a construction that achieves this bound? But it seems like all that Wagner knew was what happens for k equals 2 and 3, and from that he just interpolated. So there is very little evidence for this conjecture, and I don't believe it's true at all. But this conjecture of Jarfash and Lyle seems, it seems to be more true. But in general, the best known upper bound in any dimension, or also for a long time, it was due to Carey, who proved that fdk goes almost linearly in k in every dimension, but you have this additional log k to the d minus 1. So this argument is also kind of nice and kind of simple. So let me show you this as well. So let me just prove this theorem. So again, let's look at the same configuration we had before. Now the idea is the so-called divide and conquer argument, which is very widespread in combinatorial and computational geometry. So the idea is that if you have a problem, you want to divide it into smaller subproblems. In this case, what you can do is you want to cut the family of boxes into 2 parts, so that you want that if you look at the boxes that are completely contained in one of the parts, let's say in the upper part, there are at most k, there are exactly k over 2 disjoint in the upper half. But then because any box contained in the upper half is disjoint from any box contained in the lower half, you get that the number of disjoint boxes in the lower half is k over 2. But then what you can do is first you look at the upper half, you can find at the k over 2 points that pierces all the boxes that are strictly contained here. Similarly for the lower half. But then you still have to deal with the boxes that intersect your hyperplane. But now everything that happens with the boxes that intersect this hyperplane is actually decided on just the intersection of the box and the hyperplane, which is a family of d-1 dimensional boxes. So as you know that there are no more than k disjoints, it is enough to use at d-1 k points to pierce all these boxes that intersect this hyperplane. So in conclusion, you get the following kind of recursion inequality for fdk. So fdk is at most fd k over 2 plus fd k over 2 plus fd-1k. And now using that, we know that f1k is k. Can show that the best function that satisfies this recursion is this function, and this is the whole proof. Okay. So now this result of Carey was the best known for 25 years until actually in 2 dimensions it was improved by Correa, Falulole, and Perez-Lantero. So they proved that in 2 dimensions you actually have k times some double logarithmic factors. So here in 2 dimensions you have k log k. And actually using the previous divide and conquer arguments, but now using this new result for T, you get the following general result in any dimension d. So you get k times k to the d-2 times some double logarithmic factor. Okay, but what's known from below? So it was actually widely believed that in any dimension, k should be linear. So this conjecture was formulated in the survey of Echo, but there were hints already in previous papers. And there is actually a lot of support for this conjecture. For example, Chudnovsky, Spirkle, and Zerby proved that if all the boxes are cubes, meaning that the boxes have equal side lengths, then the conjecture is true. They also considered some special cases where you assume something about the intersection pattern of boxes, like you tell how many vertices can one box contain of another, and in this case you also have linear or close to linear. So in general, it was believed as linear. So it's somewhat surprising that I found a construction which not only shows that starting from D it's not linear, but actually it turns out that this upper bound you get from this divide and conquer argument is almost sharp. So I managed to find a construction which shows that this upper bound is sharp up to double logarithmic factors.
So it starts to work with d equals 3, right? So d equals.
Yes. So it's true for d equals 2, but then it only gives linear.
Right. So then because of this log and so on, it still might be the case that in d equals 2 is special and the answer is linear. Or what do you believe?
Yes. So this conjecture of Wagner is still true, but I actually don't believe it's linear. But yeah, I don't really have a good idea. Okay, so this was the first problem I wanted to talk about. Now let me move to another problem, which is about coloring problem for boxes. So now the setup is the following. We are given a family of boxes, and we want to color them with as few colors as possible, so that if we have 2 boxes that intersect, then they receive different colors. So again, looking at the same configuration, this is coloring. So the green boxes are disjoint, red boxes are disjoint, blue boxes are disjoint, and you can easily check that you need at least 3 colors. 2 are not enough. So this is actually the same problem as that. So you can define the so-called intersection graph of boxes, which is you put a vertex for each box, you put an edge between two boxes of the intersect, and you are just asking what's the chromatic number of this graph. Now, of course, this chromatic number can be huge. So if all your boxes intersect, which of course can happen, then you need at least as many colors as the number of boxes. So to make this question interesting, we assume that you don't have a large set family where any two of the boxes are intersect. And now ask that, can you color them with the number of colors such that this number only depends on this maximally intersecting family. And this result in dimension 2 is actually a quite classical result of Istvan and Grunbaum. So they prove that so again, just in a D equal 2 case, if your family contains no k pairwise intersecting members, then it is enough to use roughly constant k-square colors. And why the reason this result is fairly important is that it kind of started this new chapter of both of combinatorial geometry and structural graph theory called chi-boundedness, where they studied a problem that given a graph from some family, then is it true that its chromatic number can be bounded by just its clique number alone? And now there are many results showing that this is true. There are many results that show that it might not be true, but this theorem kind of started all of this. So now we are going to consider the following function. So GDNK. So this will be the minimum number of colors needed to color every family of n boxes. If
these are very weird.
family contains no
there are bubbles inside them. There is no.
Sorry. Yes. No. Istvan?
Yes.
Yeah, some kind of I don't know, some glitch on the system, right? We're occasionally getting it. No, right. You can continue.
Okay.
Right.
So this is the definition of the function. I hope it's clear. So again, in just one dimension, when we have a system of intervals, we again have that G1 and K is just K. So if you have no K pairwise intersecting members, then you can color your intervals with K colors. But in other words, intersection graphs of intervals are perfect.
Right. So just to maybe to say it, right? So basically your problem is that you have this geometric graph, its clique number is K, and you're trying to get the best bound on the chromatic number as a function of this clique number, right?
Yes.
Mm-hmm.
And so in 2 dimensions, this previously mentioned result of Istvan and Grunbaum say that it's at most quadratic. And this was the best known bound for 60 years when Ramsey and Wolczak managed to improve this to K log K. However, from below, it's still the best known construction is linear, so there is a logarithmic gap. However, in general, surprisingly, it turns out that this GDNK cannot be bounded by K alone. So here in dimension 1 and 2, we had this nice situation that this function didn't depend on M. However, starting from dimension 3, this function must depend on M. And there is this famous construction of Berling, which is used in a lot of other places as well, shows that there are triangle pre-intersection graph of boxes in R3, where you need at least log n colors to color them. On the other hand, in general, the best known upper bound is this. The GDNK is K log K log n to the D minus 2, where does this bound come from? So here, this K log K bound comes from the 2-dimensional case. And now you can use a very similar divide and conquer arguments I showed you before to show that anytime you add a new dimension, you might get an extra log n factor. So now instead of log K, you are unfortunately gaining a log n factor. And this is the best known bound. And so I can show again that But actually, this bound is not that far from the truth, at least when k is some very slowly growing function of m. So I can show that whenever k is at least log n, then there is a construction where you have no k pairwise intersecting boxes, but you still need at least constant k times log n over log n to d minus 2 boxes. So you get a very similar bound as before, and you have a tight relation up to double logarithmic factors.
So Istvan, so in particular, you beat Burling in 3 dimensions, right? By quite a lot, right?
So unfortunately here, it was important for them that this is a constant, that's 3. So I need that k grows with n a bit, unfortunately. So it's actually a very nice open problem whether you can beat this log n, because also for here the best known upper bound is just log n. And as this graph had many applications, it would be interesting to improve this. And so the final problem I want to talk about involves the Ramsey number of configurations of boxes. So in general, the Ramsey theory studies the question is that given a graph, what is the size of the largest clique or independence that you are guaranteed to find? And in general, you know that the answer is logarithmic, but when your family, but now we know that when your family is somewhat structured, you can greatly improve this. And people study that for given families, how much you can improve this. And so another question we are going to consider is that given n boxes in RD, at least what is the largest subfamily variant that you can select such that either any two are intersecting or any two are disjoint? And so then usual configuration. So here we can select these two that are disjoint, but we cannot select 3 that are disjoint. And we can select these 3 that are pairwise intersecting, but we cannot select 4. So in this case, this Ramsey number will be 3. Now, so this problem was first studied by Larman, Matishek, Pak, and Tilici. So they proved that every family of n boxes in RD contains almost square root n size subfamily. Everything is either pairwise disjoint or pairwise intersecting. But again, they have this extra log n to the minus d minus 1 over 2 factor, which again comes from divide and conquer argument. So let me introduce this function. So this HDM. So this is the maximum case such that any family of n boxes contains either k pairwise disjoint or k pairwise intersecting numbers. Then one-dimensional case is again very simple. Here we get that it's exactly square root n. Now in HDM, it's easy to show that it's at most square root n. So the usual construction is that you take you put your boxes into separate kind of cliques, and within each clique, any two of the boxes are intersect. And if you choose square root n cliques and inside square root n boxes, then this gives you exactly this bound. So square root n is somehow this very natural barrier. And then the lower bound is, so this is the lower bound I showed you before, and this can be slightly improved using this result of Correa, Falulale, and Perez-Lanterot. So you can get an extra square root log n factor. So while this does not seem like much of an improvement, this slightly improved bound is actually sharp up to double logarithmic factors. So I can show that there is a construction of boxes where you don't have this subfamily pairwise disjoint to pairwise intersecting with more than square root n times log n to the minus d minus 2 over 2 elements. So these three problems are what I wanted to talk about today. There are some other results involving Zorankiewicz type problems and separation dimension sum, which can be used, but to talk about that, I would rather talk about how this construction actually looks like. Okay. actually, all of these results follow from the following theorem after some slight modification. So I proved that there exists a family of boxes in RD such that there are no more than constant log n over log n intersecting members in it, and there are no more than constant n log n over log n to the d minus 1 pairwise disjoint members. So in terms of intersection graph, I show that you can find an intersection graph of n boxes with clique number roughly logarithmic. Independence number is roughly n to the log n to the minus d minus 1. And then it's actually not hard to deduce previous results from this, because so somehow all these three problems involve the following parameters of the intersection graph. We are interested in the chromatic number, clique number, independence number, and co-chromatic number. So, but if you know the independence number, so if you have an upper bound of the independence number, that's a lower bound of the chromatic number, and so on. So from this, you can actually get everything fairly easily. And so how does this family look like? So let me show you a picture in 3 dimensions. So this is an instant of the construction. So at first, if you look at it, there might not be much structure. It seems fairly random-like, and if you think that you're actually not far from the truth, this is inherently a random construction. But then the question is that what's the probability model from where you get this? So let me try to show you this family in a slightly more interactive way. So here is this family of boxes. And as you can see, you have boxes of different colors. And actually, these colors have meaning. So now if I just keep the green boxes, they all have the same size. I have these blue boxes. I have these gray boxes, and so on. So each color represents one type. And other than that, so I have the following rules on this construction. So I want that every box has exactly the same volume. So again, these green boxes, they have the same volume as these gray boxes. And also the other rule I want is that their side lengths are very exponentially. So I pick some positive integer, and boxes are going to be the sides of the boxes are going to be powers of this integer. And then I kind of squish all these kinds of boxes into unit cube, and then I take a random sample of this with some appropriate probability, and then this will give what I want. So just So let me give you some exact parameters or some more mathematical description of what I'm doing. So here I just show you this. So yes. So what I will do, I will fix 2 positive integers as some case, and I will consider only boxes of the sizes as to the minus t1, as to the minus t2, dot dot dot, as to the minus td, where these t1, td sum up to k, and they are integers. So this quality ensures that all these boxes have the same volume, and this volume will be exactly as to the minus k. And now, because I have this 1 over an integer side length, if I fix d tap to t1, td, then all these boxes will so I can find the partition of the unit cube into boxes of this side. And so S will be roughly logarithmic in n, and k will be roughly this. And so, for example, here is a partition of the unit cube into boxes of size 1 over 9 times 1 over 3. So it's 1 over 27. So here I take S equals 3, and I take K equals 6. And so now these colors denote something different than before. I just use so that you can differentiate between these boxes. But then what I do, I will take all these boxes, all these parameters, and then I will take random samples. So I will keep each of these boxes with some fixed probability P independently from each other. And then this will give my construction. So now you might wonder that why does this random sampling work? Why do I need this random sampling? What's the idea behind this?
Sorry.
Yes.
Do you keep all of the partitions, or you sample some partitions here?
No, so I take all of these d tuples which satisfies this. This will be roughly d to the k.
Yes.
So I will have roughly d to the k partitions, and I take all the boxes and all the partitions, and I randomly sample from them.
Mm-hmm. Okay. Thanks.
So why does random sparsification help? What's the idea behind this? So suppose that you have a graph which satisfies that its independence number, so this is alpha g, times the clique number, which is omega g, is roughly the number of the vertices, or even larger than the number of vertices. So we think of these graphs as boring because they are very easy to construct. Some perfect graphs have this property, and few tell a first-year university student to construct some graph, then most likely will construct a graph which will have this property. And indeed, if I wouldn't do the random sampling, I would just take all these boxes from all these partitions, then the intersection graph would satisfy equality here. But now, how can we make a boring graph interesting? Let's just sample the vertices randomly with probability P, and let's consider what happens with the resulting graph H. Now, first of all, we want that the number of vertices drops by a factor of P. This is actually automatic. This follows from any concentration argument. We also want that the independence number drops by a factor of P. That's the one that the clique number drops by a factor of P. Now, if we can achieve that, then actually what we have then is that the independence number of H times the clique number of H is roughly P times the number of vertices. So we gained an extra P factor here. So it immediately made our graph interesting. And it's it's of course not a new idea. We already knew that the best way to construct graphs with small cliques and independence is to use randomness. And here we just take randomness, but we have to find the right post graph. So now while this first thing is automatic, for the second and third thing, you actually have to work, and whether it's true, it very much depends on the structure of the graph and the P you choose. And indeed, this is what I do. It turns out that this family of boxes has a rich enough structure so that I can show this. And so I don't really want to go into too much details about the proof,
But Istvan, can I ask a question? So you need them to know, like you can have a graph where there are really many independent set of maximal size, and then can be a problem, right? So you really need to know, right, the numbers, and this you can.
So you really need to know the graph, because, for example, if your graph was perfect to begin with, then you can sample however you want your graph still be perfect. So you cannot have this. But so let me just give you the rough idea how to show this. So the clique number of the construction is fairly easy to handle, because as I said, we had this Halley type result that any family of pairwise intersecting boxes can be pierced by a single point. So you can identify maximal cliques by this point that pierces them. So actually you have very few maximal cliques. And then this random sampling will work. Now, the more problematic part is the independence number. And here you can proceed actually two ways. So the first one is the fairly standard so-called graph container method of Clayton and Winston. And for that to work, you need to prove so-called supersaturation result. You can do that and you will get the result that you wanted. But then there is actually a more elegant, more combinatorial proof, which was brought to my attention by János Falk and Gábor Tárdos. So they observed that actually your graph is the union of a small number of complete bipartite graphs, and you can use this information to find a very simple bound on the number of maximally independent sets, and then again just use concentration result, and that's it. So proving this would take some time, but I'd rather skip it. I don't want to go into details. So rather, so let me actually finish my talk with some open problems. So let me recall some of the things I've already said. There was, first of all, this conjecture of Gyárfás and Lehel that every family of rectangles with no k-pairwise disjoint numbers can be pierced by linear number of points. So there was this even more precise conjecture of Wagner that this OK can be replaced with 2k minus 1. But again, I don't believe that to be true, but this actually might be doable. I'm not even sure if I believe this is true. Another problem that remains is that what happens with the coloring problem where you have dimension at least 3. So my construction starts working when the number of intersecting members in the family grows at least a tiny bit with n, at least with logarithmic n. But then the following still remains is that can you find a family of n boxes in RD such that you don't have 3 pairwise intersecting members, but still every proper coloring requires a polylogarithmic number of colors. So again, the currently best known bound is this Berlin graph, which gives log n. So even just improving log to anything would be very interesting. And even not only in dimension 3, but maybe dimension 4 is a bit simpler. And finally, let me recall this Ramsey problem about boxes. So Zlárma, Matysiak, Park, and Tiracsik showed that every family of rectangles contains square root n over square root log n members that are either intersecting or pairwise disjoint. But now the question remains that can you remove this square root log n bound? So again, my bound starts to work from dimension 3, so this conjecture still remains open. And actually, this is all I wanted to talk about today. Maybe it was a bit faster than I expected, but thank you for your attention.
Okay, so thank you, Istvan. Questions?
Is it easy to explain why this sort of stuff doesn't work when d equals 2?
Yes. So maybe to show you. So actually, what you get in d equals 2 is a comparability graph. So this, if you look at all these boxes or all these partitions, they will form a comparability graph. So no matter how you sample, you won't get anything interesting out of it.
I see.
Potentially, it can be that dimension 2 is different, right? Like, for example, right, in discrepancy equations, right, there are other things that maybe in dimension 1 for sequences things behave, right? So like logs might come up later, right? It can be that it appears, right, in small dimension you don't have them, right?
Yes. So exactly. For example, epsilon, that's also in 2 dimensions you have log, and in 4 dimensions you have log. So, and it's known that it's tied there.
Can you quickly say, right, so again, this lemma which you mentioned. So again, the setting is I have a graph which is union of few complete bipartite graphs, right? And then if you, from here, right, so there's this argument which you said Janos and Gabor suggested to you, right? So you have a graph which is union of, disjoint union of complete bipartite graph, right? And then
H disjoint union.
H disjoint union. And then you want to say that it doesn't have many maximal independent sets.
Yes.
And
Because every maximally independent set looks like that. You choose one of the sides of the bipartite graph, and then you are not really taking an intersection, but from some logical operation you get an independent set, and it will be all the maximum.
and because the number of such graphs is small, so this gives you the count.
Yeah, it will be actually just 2 to the number of bipartite graphs.
I see. Very interesting. Yeah, very nice. I see. That's a good
I
one.
also didn't observe.
And why these graphs are the union of complete bipartite graphs? Is it easy to see?
So where you get them is that if you, for example, in this picture, you look at, let's say, the green and the blue, there is a smallest box that contains both of them, and that box will give a complete bipartite graph. So if you look at the smallest box that contains both a green, both a blue, then any green and blue inside will intersect. This will give you the bipartite.
I see. But then you get several of those, right? It's not that there would be a small box which contain all greens and all blues, right? So you will.
Yeah, yes, you will have several.
I see. But I see. It's still good now.
So actually, that's why. So here, that's why you take S. So that because usually you would take some binary thing like these dyadic boxes, but this doesn't work. So that's why you need to take S to be polylogarithmic, so that you push down the number of these complete bipartite graphs. Because then the smallest box will be S times larger at least than both these smaller boxes.
I see.
Istvan,
Yes.
so where does the double logarithm come from in the denominator of K?
Oh yeah, it's because S is log, so I look at what power do I need to take it to get N. That's where log comes from. So if I could take binary, then it would be just log.
Sorry, I don't understand. Could you say it again?
So if in this construction you could take S equals 2 or just any constant, then you wouldn't need this log, and you would get the optimal optimal thing. But so maybe you can work with that as well. I couldn't see a way to do that.
Okay, thank you.
Okay. More questions?
Hey, Istvan, maybe a silly question. Maybe I slept through it, I don't know. But for the original question, for K equals, oh no, sorry, for 2 dimensions, there was this bound of 2K minus 4 or something.
Yes.
So these are, so this is the best we know so far for 2 dimensions, right?
Yes, and it's an exact construction. So it's not very complicated.
Okay.
Yes. Very nice. Any questions? Great. So thank you, Istvan. So it was really nice talk and very exciting results, right? So I hope the open problem will encourage people to think about them. So we can stop the recording.